Hi, I'm Ken, and I hope all your projects are going well today. Well, this is my first YouTube video, and what I like to do is take you through my modification of the Harbor Freight Chicago Electric Flux125 Flux Core Welder to operate from AC and convert it to operate on DC electronegative. Now, I got this on a very good sale price for $37, which made this a very cost-effective project. Well, this is my take on doing this modification. So let's take a look inside and see what the mods look like. I had most of what I needed in the parts box. I did have to order some number 6 flexible welding cable, and this will be used in the welder for the wiring as well as to wind the choke coil. I'm going to use number 6 wire instead of number 8 because 10mm square wire is used inside the welder now, and that's equivalent to about a 7 wire gauge, and the 6 is slightly thicker than the 7 wire gauge, and 8 is slightly thinner. So I'll use the step up. If you use the number 8, it's not a problem. The 8 should handle the current and voltages that are present in the circuit, so that should be fine without any problem. I have this 4.5-inch ferrite toroid core, and this will be used to wind the choke coil. I'll put as many turns of this number 6 wire as I can around this core, and if I had 2 of these, it would actually be preferred. The thicker the core, the better. The more mass it has, you get a better magnetic field. I have a much smaller 2.5-inch choke. Some of you have used this, and I won't get nearly as many winds around this with the 6 cable as I will around the larger core. So I use that for a secondary coil if you know, just to experiment with. I'm going to use a 200 amp bridge rectifier. I prefer to use this. It'll have a little bit better heat dissipation and heat handling capability than the 150 amp, and certainly preferred over the 100 amp that some have used in the project. So this, along with nice heat sink. I have this from a computer project from a number of years ago, and this would sit on top of the bridge rectifier. This can be mounted upside down, not a problem, and this will help dissipate the heat. Heat is the enemy of electronic circuits, so the better you can handle and dissipate the heat, the more reliable the circuit will be. Recommended to use thermal conductive grease between the surface of the bridge rectifier and whatever heat sink is used. For the capacitors, I had a number of these electrolytic can capacitors in my box. These are 22,000 microfarads at 50 working volts, and I put 3 of them in parallel for 66,000 microfarads. And to make things a little easier, I ordered a 20,000 microfarad 50 working volt capacitor with the screw terminals. This also came with a bleed resistor. This is 1,000 ohms at 5 watts, and this will help to dissipate any residual voltages in the circuit. So this is a total of 86,000 microfarads, and these capacitors here, which makes them a little more difficult. These are solder leads These normally get soldered onto a printed circuit board. I prefer to use the screw leads. They're easier to deal with. One thing I need to keep in mind is have a polarity, and you need to connect the positive to the positive, negative to negative. I'm going to upgrade the power cord from number 16, which Harbor Freight uses in the welder, which is marginally sufficient for the welder. 14 gauge would be better. A couple dollars more, Harbor Freight, and more reliability, less voltage drop. So number 14 wire with the 9-foot cord. If you go with a 25 or 50-foot cord, if you want to extend the reach of the power cord, then go with a number 12 or number 10 power cord. So then some odds and ends, some lugs for the 6-gauge cable, spade terminals for the power cord, some star connectors, star washers for the connections, as well as some shrink tubing of various sizes for insulating the connections, as well as some various types of electrical tape. Here's the Eastwood MIG 135. Let's take the cover off and we'll see what's inside of the welder, which is a true DC MIG welder. Let's get some light. Here we have the bridge rectifier, which changes the AC to DC with a large aluminum heatsink on the front and an equally large plate on the back. We have the power transformer, which provides the proper current and voltages to the welder, and we have the choke, which helps to filter out the AC ripples, and we have a capacitor which smooths out the voltages. Let me zoom in on the choke coil a little bit here. You can see that this is wound around a laminated core with some large flat conductors. And here's the electrolytic capacitor. Then this is a 72,000 microfarad 40 working volt 50 volt surge screw type electrolytic capacitor. So the voltage flows from the transformer into the bridge rectifier, converted to DC. In parallel with the rectifier is the capacitor, which filters out the ripple voltages. And then the positive is fed through the choke and into the positive lead of the welding cable with in this case is the welding electrode. Because the gas type MIG welding is done DC electro positive. We're looking down into the top of the MIG 135 welder. Because this is a shielded gas welder, we have a gas solenoid which is actuated by the trigger on the welding torch. The front of the bridge rectifier has an equally massive rear aluminum plate on the back of the rectifier, quite a bit larger than what we use in the Harbor Freight mod. We also have a vane axial fan back here, if you can see it, that provides cooling for the welder. On the top we have the circuit board that controls various functions of the welder, wire speed, voltage controls, and other functions. Very nicely laid out, very neat wiring, and they actually use number 7 wire gauge 10mm square welding cable inside the welder for circuitry, and various sizes for other support circuits within the welder. Okay, I finished the work on the mod. Took about 3.5 to 4 evenings, and I've tested it out. I have about 10 minutes of welding time, and it works as good as expected. Actually, it works very well. So let's take a look inside and see what it looks like. Okay, this is the feed side of the welder, and this is the cable for the electrode, and the wire feeds up here. This is the ground wire. I put the 4 capacitors on this side. There was plenty of room to mount the bottom bracket for the capacitors, and I have these other 3 smaller capacitors silicone down, so everything is in there nice and tight. It's not going to move around. So the bleed resistors, I found that the 1000 ohm bleed resistor that came with the can that I bought on eBay was a little bit too large, so I had some 50 ohm 10 watt capacitors, and I put 2 in series to make 100 ohms, and this seems to be about the right amount of bleed for this 86,000 microfarads of capacitance I have here. The 1000 ohm took about 170 seconds to bleed down the voltage, so it would still spark. This takes about 4 or 5 seconds to bleed down. You don't want to use too small or too large the value of resistors. Too large and you won't bleed off the voltage, and you'll still get some sparking at the electrode. Too little resistance, and this actually creates a little bit of a load, and you wind up creating heat in your resistors, which really translates to using up some of the amperage that should be going to the electrode. So there is a formula that I'll put on the screen to calculate the time constant for the capacitors you have, and what kind of resistance you need to bleed off your voltage within the time frame that you want. And then you can use Ohm's law to figure out how much amperage is actually going through this small circuit here as well. But anyway, I found that 100 ohms is the right value. Negative to negative, positive to positive, and the capacitors are in parallel with the circuit, so I ran these 2 wires over to the rectifier, which I'll spin the unit around, and we'll take a look at the other side. I did change the cable here to number 6, the welding cable, the stranded welding cable, and that comes directly off of the choke coil, which I'll show on the other side. But the cabling was a little tight, but that's why you need to use flexible cable, because would be a real bear to try to use very, very stiff cable and get everything inside the cabinet and connected properly. So I always like to cut things just a pinch too long than too short, and then feed it through and route the cables in a way that they don't interfere with each other or create some sort of a shorting hazard. So anyway, this is, let me just light up things here a little bit better so you can take a look at the top. Just want to point out that one of the improvements I think that Harbor Freight has made is that this is a 24 volt regulated DC motor that is running the feed now for the wire, and there is a circuit built in here to regulate the voltage, and I think it does a very nice job to the feed speed fairly consistent. So I think in the past they used an AC motor, and now this is a DC 24 volt DC regulated motor, and it's been very consistent. Another thing I want to point out, and while I have you on this side, is that one of the really good features that Harbor Freight is including now is that they're using a notched feed roller, and this is the roller from my Eastwood, and it comes with a plain groove for the feed. The Harbor Freight, and I don't know if this is going to show up on the video. I'll see if I can get a close-up picture of it. But there's notches in the grooves of the feed roller. And this acts, I guess, like snow tires during the wintertime gripping into the snow. So if you have ball tires, it's not going to grip the road very well. But these notches here help to feed the wire much more smoothly with much less chance of slippage. So it has a nice indexed shaft and a little locking cover, and it's a very nice little setup here. It's an improvement over what people have shown in the past versions of this welder. So let's spin this around and look at the other side. Okay, this is the other side of the welder. As you can see, there's much less space on the side of the cabinet to mount the capacitors. So the other side is the side of choice for the cans. The choke, there's plenty of room here in the front of the welder to mount the choke coil. This is 5.5 inches, and I have it mounted on a small platform there to allow some air circulation and to keep it off the bottom of the welder. A little bit of jockeying to get these wires out of the way and to create some space there, but not a real problem. There's sufficient space. So what I have here is 25 feet of cable, and I removed the outside insulation that's on this Tough Flex 6-gauge cable, and I insulated it with electrical tape, and this decreased the diameter to allow for about maybe another 3-4 turns of wire around the core. So I have about 15 feet of wire around the core, and then the remainder of the 10 feet exits the front and comes out to the ground clamp. So this is on the positive lead of the bridge rectifier, and this is the positive part of the circuit is the clamp, and I used the Lincoln Electric 300 amp clamp. This is a much better improvement over what was originally on the welder. This has a nice bonding conductor between the upper and lower jaws of the clamp, as well as some beefy copper coated parts of the clamp, and a nice heavy duty grip as well, and nice bolt. So anyway, that's one continuous run all the way from the DC part of the bridge rectifier. As you can see up there, it loops around a little bit to the choke, and then 34 turns, 35 turns, whatever, and then over to the clamp. So whether it's on the positive or negative part of the circuit, that's a matter of opinion. I don't think it really matters. It's all part of the same circuit, but it seems to do the job. It does filter out the current ripples, so it works. I also upgraded the power cord, as I mentioned earlier, and here's a continued part of my rant against the 16 wire gauge. Here's a little bit of, for those who need to know this, 16 wire gauge is very, very thin stranded wire. Here's 14 wire gauge. Still not as beefy as 6 gauge, but it's certainly an improvement over the 16 wire gauge. So 14 wire gauge, 16 wire gauge. They use 14 gauge, and it's marked 14 wire gauge here in the primary part of the circuit. So why not match what's in the welder to start with? As far as the DC, the bridge rectifier, I mounted this to the top of the welder These are the AC leads in from the transformer, and a nice tight crimp connections from the transformer. Anyway, so ran them up to the welder. The DC out is on the other part of the on the inner part of the bridge rectifier. I mounted this directly to the metal of the metal frame of the welder. I did remove the paint on the top and the bottom. The top surface here and the bottom surface down here. So this remove the paint. I used some conductive grease to increase the heat transfer efficiency between the bridge rectifier and this heat sink. So, and this is bolted down very, very securely. I could lift the welder up from this if I could here. But the heat transfer here during my 10-minute test, this got warm to the touch, but not really too hot, and you could feel the heat being transferred up from the bridge rectifier into the heat sink. But it didn't get hot. It wasn't broiling hot by any means after 10 minutes of welding. This vane axial fan, which is an upgrade from the disc blade fans that were in the Flux125 welder, provides a lot of flow, and there was a nice breeze across the transformer and underneath and through the holes in the bottom of the welder. So airflow shouldn't be a problem, and the cans, transformer, the core, everything was fairly cool during the 10-minute test. If you're thinking about doing the modification, go ahead and give it a shot. I'm very satisfied with the results. Follow standard wiring practices, and I go a little overboard with electrical tape, and it's cheap enough, and I like to prevent braiding and metal to metal or metal to wire contact as much as possible. In the next segment, I'm going to compare the welds from the Eastwood True DC Welder in gas and flux core mode, along with the pre and post for the Flux125 after the DC electronegative modification. So that'll be the next segment. Okay, I'm going to do a test weld here so you can hear how it sounds. I'm not sure how this is going to come out. This is the first time I'm trying to weld on camera. So let me give it a shot. Okay, let's take a look and see what this looks like. Okay, let's give this a little cleaning, see what it looks like. Give it a little zip with the wire brush here. Okay, let's take a little closer look at that and see how it looks. Okay, this is the post-mod DCEN weld with the Harbor Freight Flux Core 125. This is using the 0.03 Flux Core Vulcan wire, and it looks pretty good to me. It sounded good. There's a couple of moon craters. I could have used a little bit less heat, I think, in the weld, but minimum of BBs. And for do-it-yourselfer at home, in the workshop, I'm certainly an amateur welder. This would get the job done. After I finished the mod, I did extensive testing. I welded for about 10 or so minutes straight, pretty much without too much rest. And I'm very happy with the results. Welds were consistent. Of course, you get some BB still, but not nearly as many as pre-mod. So all in all, I'm happy with the results. For comparison, I did a test using the MIG 135 with the shielding gas, and I used .025 Lincoln MIG wire. I find that using the shielding gas, it's a little easier to control the puddle, and the welds come out pretty nice with minimal cleanup. This is using a wire brush, but the welds don't have any slag on them, and I find it's easy to control the puddle, also to get a nice smoother weld. It takes some practice using a flux core wire, whether it's the Harbor Freight or the Eastwood. It's possible to get a really nice looking weld either way, but as I said, it's easier with the shielding gas. And with the shielding gas, you have to do that inside so that the wind or air currents don't blow the shielding gas away. And that's one of the advantages of the flux cores. You can use it outside. Here are some test welds I did before the mod. On the left is the HF Flux125 in AC mode, and on the right is the Eastwood MIG 135 in DCEN mode. And I use the Vulcan Flux Core .03 Flux Core wire. Let me zoom in, give a little bit better look at each of the welds. Get in focus. There we go. And this is the Harbor Freight Flux 125 in AC mode. And this is Eastwood in DCEN mode. Let me flip them around and I'll show you what they look like cleaned up. And this is using just a wire wheel to get the residue and the slag. The brown residue is typical of the Harbor Freight Vulcan Flux Core wire. Now this is the Harbor Freight Flux 125 after cleanup. And this is the MIG 135 after cleanup. Well, thanks for watching. I hope you got something out of the videos. I really enjoy doing this mod. So if you liked the video, press the subscribe button below. I'm working on a few more projects and hope to get a couple more videos posted soon. So thanks for watching and hope all your projects go well. And I'd like to show you the, for God's sake, supply. But there are many very good videos on YouTube.